So, okay, so for information, to make it, to grow your tree, right, we have to make these decisions. And we're going to use something called information or information gain. And this tends to be actually relate really well to a concept called entropy. Kind of quick thumbs up. Who's like maybe familiar with the word, like at least heard the word entropy before in this case? Okay, see some thumbs up. Okay, yeah, see some thumbs down. That's okay. It's a very scientific concept. In physics in particular, it's useful for a lot of things. It's kind of abstract, to be quite honest, but it's useful in this case, and it turns out to be really common. But if I were to tell you, like, maybe think back to like if you, for Andy and Jenny who have heard it before, if I were to ask you like vaguely, like define what entropy is based on like maybe like your high school or college like class, like what comes to mind? Like what kind of phrases? I don't know. This is a shot in the dark. I don't know if anyone would actually think this.
I always think of chaos. Like when I hear entropy, I think about chaos. But
Yeah.
I can't think of anything beyond that.
Yeah, yeah. Yeah, I think that's classically, and I saw Andy kind of make some nods there. I think classically everyone always goes like, it's chaos, or, what's it called? Disorder, I think usually. Like entropy measures disorder. And I think this is where it gets really confusing. Like, for example, in physics, they talk about entropy always increasing. People say, oh, disorder, things get messed up. And that's not exactly what entropy is. It's close, but we'll kind of talk about what that is. And I think that's important to say, how do you make these decisions for, this will actually tie into how decision trees make those decisions. Basically, it wants to lower entropy. So I'm going to go through a little bit of concept of what entropy is, because I think that's kind of useful. So like the way I kind of define entropy is basically, it's different ways to organize your stuff. So like how many different ways can you rearrange like your junk? So people tend to say like, oh, if it's like really disordered, it's high entropy. And it's like, that's kind of related, but it's more about saying, what is possible for you to rearrange? Like, if I rearrange this, would you be able to tell there was a change? That's really what entropy really is describing. So again, sometimes references disorder, since disorder gives just many more options. So imagine if like I messed up your whole room, right? And then like I came back the next day and rearranged things. You might not really be able to tell like, was your room really changed because it was already super messy, right? But if you had a really nice, clean, pristine room and I moved like one thing, you would know that one thing was moved because everything's already clean, pristine. So I think that's where the connection comes from. And we would say that the messy room, because it has a lot of like, just movement, like a lot of different arrangements that are kind of like indistinguishable from each other, we say that's high entropy. And something that's already like really well arranged, and we take one little thing out of the way, and now suddenly we know it's not the same as before, like it's very obvious, we call that low entropy. Okay, does that kind of make sense to people? Okay, I know I'm talking very like abstract right now. So we'll kind of simplify it a little bit further. So imagine instead we have something like different like colored balls. We have either a blue ball or a red ball. And say we have 5 of them. And so we can think of like saying, how many possible ways are there to arrange 5 identical blue balls? So like imagine putting them in some kind of order. How many different ways can we put 5 identical blue balls in order?
1.
1, right? Because they're identical, right? There's no way to really tell the difference. So we would say 5 identical blue balls are basically a lower entropy. So there's only one possible way. There's basically in low entropy state. If we say there's 4 blue balls and 1 red ball, right? How many different ways could we rearrange that case? Good, 5, because there's 5 different places that red ball can go, right? So that has higher entropy. And then you can imagine, say, going from like 3 identical blue balls to 2 red balls. We don't talk about the exact number of this, but basically you can say, okay, well, I can take those 2 red balls and place them in different spots. So you can have 2 in the front, 2 in the middle, 2 side, towards the end. You can separate them out. So there's going to be more possibilities. So this would have a higher entropy. Okay, so that's the kind of the idea here, is that when we have more possible ways we can configure these things in different orders, essentially, or not just orders, but just different like configurations, we have their higher entropy. Okay, make sense so far? Yeah, okay. Nothing too complicated yet. And look, no math yet, right? Other than just kind of counting. So, all right. So next part we have is like, okay, information. So information is going to tie really closely to entropy. And essentially, we're going to kind of use this like little analogy of like, if we were to pick a ball at random for each of the situations, could we know what ball color it likely is? So if I randomly pick of the 5 identical blue balls and I pick one out, what color is it? It's blue, right? Yeah. So like it's really simple, right? So that's a low entropy. Basically, there's nothing like to gain information. Essentially, like, oh, I pick a blue ball. It's like, oh, well, I know it's going to be blue. Like I have high information. I know this is going to always be a blue ball, right? However, I went to something where it has 3 blue balls and 2 red balls, and I mix my hand like I don't know, like a little hat or whatever where I have the balls in, and I pull one out. You don't know for sure, just by knowing the configuration, you don't know if it's going to be a red ball or blue ball. You kind of have some suggestions like, well, it's going to be slightly more likely to be a blue ball, like 60% of the time, but 40% will be red, right? It's like, well, I kind of don't know. And so we have less information by knowing the configuration. So that's kind of the idea of like more information versus less information. And this is the idea where basically they're converses of each other. If you have low entropy, you have high information. If you have high entropy, you have low information. Make sense? Okay. So this leads us into now the actual mathy kind of stuff. So, oh, actually, no, I got another situation. Good. So I'm really trying to hone in, like, understanding this because I think like it's important to like really understand it before we talk about the math. So this is where I think, oops, why does this come out right? Oh, well. Okay, Markdown didn't like me. But anyway, so there's a little situation, and this is going to lead us into how we're able to quantify this entropy and information. Because in the end, we'll actually want to say what is a higher entropy from each other. Like we want to be able to quantify this. So we're going to have a little situation. We are going to draw one ball at a time and putting it back after drawing. So imagine bootstrap sampling, right? So essentially we have like our balls in here, we pull one out, we record what color it is, we put it back in, mix it up, and draw again. Okay, we're gonna do that a total of 4 times. In this case, we're gonna have, instead of 5 balls, we're gonna use only 4, but we're gonna do this for a total of 4 times. So we're gonna say, draw the ball, see what color it is, put it back in, draw a ball, see what color it is, do that 4 times. If we get the same configuration of whatever was in the hat, we win the game, okay? So if you imagine if there are 2 blue balls and 2 red balls in here, we have to draw 2 blues and 2 reds. Note the order doesn't really matter. It just means that we just have to draw in total 2 blues and 2 reds. Make sense? Okay, so if we have, but we get a little extra part in this. It's like we get to choose which situation we want to draw to up our chances, okay? So we have 3 different situations here: 4 identical blue balls, 3 blue balls and 1 red ball, or 2 blue balls and 2 red balls. So which of these situations, these configurations would you want to play with to up your chances of winning?
The 4 blue balls.
Yeah, 4 blue balls, obviously, right? Because then there's like, you're going to win like 100% of the time, right? Like there's no way for you to lose. What would be like the next best thing if like 4 blue were not available to you?
The next one down.
Yeah, next one down. And I think like, like even if we can't like really quantify this by itself, like, I think like the basic idea is like, yeah, you're just more likely to be able to draw out 3 blue balls and then 1 red. There's still a chance that you basically get 4 blue, which you'd lose, or 2 blue and 2 red, right? But it seems like more likely than compared to getting 2 blue and 2 red, right? Okay, yeah. And so this is where we can actually quantify this. So we can actually go look at the actual probabilities. So as I said before, clearly the identical, like 4 blue balls are going to be really easy to win. You're always going to win that. But we need to find, so to kind of get an idea, we can build up the probability of like how it's winning. So kind of a quick hint before we go into these other 2 situations is that in order to draw the same exact configuration, we need to multiply the probabilities for each ball, right? The probability of getting blue, probability of getting blue, probability of getting blue, probability of getting blue, right? Which is just going to be, in this case, in this 4 identical blue balls, 100%, times 1, times 1, times 1. So our probability of winning is 100%. Does that make sense? Yeah. So then the real question comes down, it's like, okay, we have these other 2 situations. How can we expand this where there's only 1 red ball? And then would the probability change? Like think of like how this probability right here would change. And then also, would these all be the same? Obviously, it probably wouldn't. Also note that we don't have to worry about the order. So we don't have to worry about like, combinations versus permutations. Essentially, we can just look at this essential blue plane. Okay, so.
Let's be like 75% to the 4th.
Yeah, so there definitely will be, the probability of blue will be 75% right here, right? So how would we modify this, like this kind of little equation right here that I drew out, where we have probability of blue times probability of blue times probability of blue times probability of blue. Let's start with that. How would we modify this for the three blue and 1 red? Well, let's go through. What's the first ball we need to draw? Or what is one of the colors that we need to draw?
Blue.
A blue one, right? So we first need to have the probability of drawing blue. Okay. And then it's going to be multiplied by the next ball. What's the next color that we would need to draw? Remember, it's out of order, but it kind of helps to think of like what would be the next one.
It could also be blue. We could go in order.
Yeah, so blue, and then the next one would be blue again. And the next one would be, in that case, red. Yeah. So we would have the probability of blue, 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 and then probability of red. Okay. And like Lauren had mentioned, the probability of blue is going to be different. It's going to be 0.75. So essentially we'll have 0.75 times 0.75 because it hasn't changed because we're replacing it, right? Times 0.75, and then just 1 out of 4 chances of picking a red one. So that one will be a 0.25. We multiply those all together, and that will give us the probability of us actually winning. Cool. So we can actually look at this then. Is that essentially that's what we'll get, is this probability of blue times probability of blue times probability of blue times probability of red. And we can see 75, 75, 75, 25 gives about 10.5% chance, which is a lot lower than our 100%, right? And you can see kind of similar thing with the blue balls and two blue and 2 red. We can see 2 blues and 2 reds, which would be 0.5, 0.5 times 0.5, 0.5. It's 0.25, okay? So that's kind of like, you can see here, it's like, all right, kind of our intuition, we already knew that the 4 identical ones are going to be the best, and then like 3 blue are going to be the second best, and then like 2 blue, 2 red are going to be like, you know, the worst case scenario. And you can see this is kind of like quantified here. So we can actually use this then to basically, this kind of example of counting probability to say, hey, that's how much entropy this is. So we can actually measure it directly in this way. So this is where we get something called Shannon's form of entropy. And note that there's one quick thing is that you'll notice that these are being multiplied together. In general, we tend not to like things being multiplied together because it's a little bit harder for us to deal with. So we actually end up doing the log of this whole probability here. So that's where actually this log comes in. Also note that this log doesn't have, technically should be base 2 in this situation, but since we're taking the log of everything, it doesn't really matter what log base you have. So in general, we'll just put log. But Shannon's entropy, I think, is binary, so it'd be log 2, but you could just easily use log 10 or the natural log. It's the same, essentially describe the same things. It's just comparing the different entropies together. Okay, so this actually, I think the curriculum kind of shows this. Note that we put a negative here. The reason I put a negative here is because the log of a number that's less than 1 is going to be negative. So we basically put a negative so we can say, okay, which one's greater? And this H represents the entropy. Or yeah, this H is going to represent the entropy of that situation. Okay, and so essentially all we have to do. Pretty straightforward, huh? Cool. So once we have this equation, then we can actually use this to say, okay, for every situation, we can say, what's the likelihood of, or what's the best way to split this? So imagine we have some decision split. We say, all right, we're going to split it on this feature. And we can say, what would be the best kind of situation to split it across? So you can imagine like this split right here is decent. But if I wanted to have even a higher, even more information, which means get into a lower entropy state, ideally what colors should be on this set 1 and set 2? Like the perfect, like, you know, amount of information, or the highest information gain we could possibly get.
I mean, ideally all the greens would go on one side and all the blues would go on the other.
Yeah, exactly. Because if we had it like all blues, like, you know, we had 5 of them over here. I think there's 5, other 7, whatever. If you imagine we had all 7 on this side on blue, and then we had the green, the 6 different greens on this side, we'd have the highest information gain possible. Basically, we went from having a mixed bag of things to, oh, everything to the left is blue, everything to the right is green. So this entropy will be smaller, basically more information gain. Okay, cool. And essentially that's what decision trees do, except that just know the decision split. It needs to decide not just on what threshold to split to give the most entropy, it also needs to decide on what feature. So it does that for every feature for that partition that's left over, and then says for that different feature, what threshold should go through. So essentially that's why like the decision trees will actually be a little more optimized and searching for that right information split. Okay, Does that make sense to everyone? Any questions on?
I
Yeah.
kind of am a little confused on your last
Mhm.
statement. Well, so like I get that. So we want to see the entropy like with the initial data set, and then we want to see it when we do the split to kind of see if we're like getting better information with our decision trees. But I guess like, what was that last thing you said about the threshold that? Like,
Oh yeah. So like if we had just like class A, like, you know, young or old, it would say, okay, should we split it on young versus old or student versus worker? Like what would be like the better feature to split? Like what would give us the most information?
okay.
But if we had something like age where it's like, oh, their ages are like 1, 2, 3, 4, 5, 6, 7, 8, you have to know like what split do we put it on?
Okay, I get that. Okay, thanks.
Okay, cool. No problem. It was kind of like the, if you think back when we were doing the, we were drawing those lines, that's essentially what the decision tree is doing. It's like, okay, like, let me just keep drawing the lines and see where it would split. Now I make it kind of like sound like it's like, oh, it's got to draw every single line and figure that out. It has a little bit of optimization to do this too. But the point is basically that's how it can determine, you know, it says, okay, let me try all the different situations. Which thing will give me the most information gain on this one split? And then it does that thing. And that's why it's deterministic. It only picks the thing with the highest information gain. Okay, cool. Good questions. Yeah. So this is, I just put this really quickly in here. The curriculum kind of goes through it, but to be quite honest, it's not essential for you to really understand this in order to like do decision trees. But you can kind of think of like decision trees when they make that decision. Essentially, they're just saying, what is the information gain? Like, what's the highest like change of information? We go from high information, and it's just the difference of the parent's entropy. So this would be the parent right here, to the average of the children's entropy down here. And note technically that it's not just the average, it's a weighted average. So if there tends to be more on one side than the other side, it's going to weight that accordingly. But the idea here is that it's going to say, okay, the entropy average for the children compared to the entropy entropy from the parent, what's the difference between those two? Okay, that's our information gain. And we're going to increase the amount of information gain we get from going from parent to these splits. Okay, cool. And you can see this little equation here, but hopefully it doesn't seem too scary now because you can see, oh, this is our entropy right here. Okay, and this is basically the entropy of our children. So you can imagine if there's like, you know, 3, 4, 5 children on one split, you would just essentially do this PT and HT, which PT is basically how many get split across each part. Note for if there's only 2, it basically summarizes to this right here, where information gain is equal to the entropy of the parent minus the entropy of the first child. And note this right here is just counting how many go on the left side and how many go on the right side. So it's a weighted average. Okay. Cool. All right. Yeah. Any questions on these last parts? Pretty good. Okay. How are you feeling on decision tree conceptually? Thumbs up, sideways. Good. Hey, those are some quick thumbs up. I like it. Okay. So cool. So we have a few more minutes, but I'll mention really quickly about hyperparameters. So, sorry. Yeah, we have enough time. But yeah, so hyperparameters for decision trees. And so I'm just going to quickly just kind of go through a few examples of what this is. It's mentioned the curriculum. I actually think the curriculum does a great job of like showing you different plots of like what that looks like. Note that you can check out the decision tree classifier for sklearn on this part right here, and you can see all the different hyperparameters you can tune right here. So you can see there's even more than the ones we were going to talk about. But the main ones to kind of consider are things like max depth. Basically, how deep can something go through? So let's say, okay, how many splits do we keep going through? And so this will obviously prevent us from overfitting, right? If we set up our max depth and we only go down 2 levels, it's not going to go any further than that. It's not going to get more complex. Obviously, if you find, like I said about the, what's it called? Your training versus your validation error. If you find your validation error still needs to go down, like it's still going down and kind of gets stopped right here, you might need to increase the max depth. Okay. Minimum number of samples per leaf. This is just the smallest number of samples you need per each leaf or each node. So essentially this is kind of like, this will overpower one of these two, right? So example is that if we need to have a certain number of, what's it called? Like we need to have this many samples in that leaf, it'll keep going until it gets to that minimum. Okay. And then you can see something similar as the minimum number of samples per split. So basically the idea here is like it won't split it unless it has this amount of number, or sorry, the smallest number of samples. Okay. And this is actually a really nice one, is that I think this is counterintuitive, maximum number of features. Essentially, it will only consider so many features. Basically, it'll go from the very most important ones, the ones that give the most information gain, and it'll kind of go further and further down. But you can kind of imagine as you get deeper and deeper and deeper and deeper, right? There's certain features, like technically it does do better, but they're really not that much more important. So this basically makes that cap right there. It's like, all right, like only consider the 5 most important features. And essentially that will limit how far it goes into it. Okay. So, and again, I really suggest like checking this out. Definitely, if you haven't gone to the curriculums lab where they talk about the different hyperparameters, definitely check that out and kind of go through it, because they kind of show a good like how it adjusts for that data set. I think they had little graphs of like, you know, increasing the max depth or increasing the minimum number, and you can see the higher complexity and like what that looks like for overfitting. Okay, cool. Yeah, so any questions on hyperparameters overall that either you see here or from the curriculum? Pretty good. Okay, yeah. Usually these are like the main 4 that you would adjust yourself. And usually for decision trees, I usually see either max depth, or sorry, max depth and maybe either one of these 2 kind of decide, because these kind of compete with each other. And then maybe maximum number of features. But usually if you set one of these 3, this usually will kind of automatically, like that, this will tend to overpower the number of features. But if you have many, many features, it might be worth, you know, just saying, hey, only consider these like 10 or whatever. Okay, cool. All right, so we only have about a minute left, so I'm not gonna go through this part, but I do have like a little decision tree code example here. And let's hear, I just wanted to kind of quickly show you guys what this looks like. But the code's here. Note that this optional section, depending if you don't have the right sklearn or installed stuff, this part won't work. But I think it's a nice thing for you to see what that looks like. So just know I used part of this. I used part of this code from like this book right here, which is Hands-on Machine Learning with sklearn and TensorFlow. I also have in here a connection to the GitHub repo, which has like some of this extra code. It doesn't have to say what's going on, but this code kind of is similar to here. Okay, so I'm just going to show you a little bit like implementing this. We're just going to use the iris data, so classic stuff. I put a train split, and essentially I'm going to say, okay, let me go ahead and train a decision tree classifier. So really simple. I only put max depth equals 2, nothing too complicated. Okay, so what's cool is that I can actually go ahead and plot this out. So if I go and plot this out like this, you can actually see the decision tree. So this is a really nice thing to have. However, you need to have sklearn 0.21, which you have to check that. I think the learn environment does have it, so just double check that. But you can basically plot out this tree and you can see how it splits off to the left and right. And you can see how many samples given each, 36, 120, 105. There's some extra stuff you can do. For example, I like this graphic right here. As you can see, is that same information, but you can see that basically all the samples are all in this certain class. For example, it's class Setosa, so 36 are in class Setosa. And for color, you can see 41 are in here, but 3 are in from Versinica. And you can see that basically it's like, oh, it's going to be mostly Versicolor. And I'm not sure if I'm pronouncing that right. And you see the other side is Virginica. Okay. This is a nice little visualization. Note for evaluation, I won't run this since I already go through. You can basically take your classifier that you already trained, make a prediction on data it's never seen before. It'll make its predictions. And then we can go through our classical, you know, AUC and like, you know, confusion matrices or ROC curves and stuff and compare basically, say, hey, you know, how well does it perform? So in this case, the AUC 0.95, so that means it's pretty decently here. And you can see a confusion matrix of where it makes the mistakes. For example, you can see, okay, for class 1, basically, it does it, or class 0 does a really great job. But it looks like maybe for class 2, it makes a mistake or 2. It looks like it makes 1 mistake here. Why is this? It looks kind of squished over. But you can see here is that it makes a mistake for class 1 and makes a mistake for class 2. Okay. Anyway, that's just kind of a quick thing. And just know that basically the training, like you can see, this is like all the code for like classifying a decision tree. So you can see like very straightforward, but the real power here I'm going to really emphasize is going to be these hyperparameters. So those hyperparameters are the things that you're going to have to tune and stuff like that to make sure it doesn't overfit. And even then you might still get a lot of overfitting, which will lead us to next times for like ensemble methods where we basically combine many decision trees and such in different models and say, all right, let's create a super, you know, model. So for example, random forest tends to do really, really well. And that's essentially because we're taking random decision trees and putting them all together in a forest and essentially make one super model. Okay, cool. All right, so I'll stop here then. Sound good?